Hello friends, so this is part 2 for the year 2022, and in this part 2 we are going to solve 7 questions from the mains and 6 questions from the advanced. So in total we are going to solve 13 questions, and this is the final part from the year 2022. So in the first question, it states that a condenser of 2 microfarad capacitance is charged steadily from 0 to 5 coulomb. Which of the following graph represents correctly the variation of the potential difference V across its plates with respect to charge Q on the condenser? Okay. So we know that the relationship between the voltage, that is potential difference with respect to the charge, and that is our V is equal to our Q upon C. And here C is given to us as 2 microfarad. Therefore we can say that the potential difference V will be directly proportional to charge Q. So we can say that the graph will be our so at least this B and D are not possible here. The only possibility is with respect to graph A as well as graph C. But in graph A, when the charge in the capacitor is given as 5, the potential difference is 2.5. So which is not according to this proportionality relationship. So option C will be our correct one. Option C is correct. Next question. It states that the volume charge density of a sphere of radius 6 meter is 2 microcoulomb per centimeter cube. The number of lines of force per unit surface area coming out of the surface of the sphere is dash 10 to the power 10 Newton per coulomb. So here we are going to find out the electric flux density, and in the simpler terms we can say we are going to find out the electric field, because it says that number of lines of force per unit surface area. Okay. So this is our, you can say we are going to find out for our electric field. And flux density is given, radius is also given. So we can say total charge enclosed, total charge enclosed, let us suppose that is given as Q. Q will be equal to our charge density multiplied by volume, that is our 4 by 3 pi r cube. So we get our charge is Q, density is given as 2 microcoulomb, and this comes as our 4 by 3 pi, and radius is given to us as 6 meter, 6 cube, and Okay, so this is our centimeter cube. So from here we get this as 576 pi times coulomb. So this is the total charge enclosed. Now we can easily use the Gauss law to find out the electric field. So we can say from Gauss law, of electric field will be equal to charge enclosed, and this comes as 4 pi epsilon naught, and we have this is r square. We substitute the value, we get of electric field is equal to, this is 576 pi, and here we have 4 pi and epsilon naught, this comes as 6 times whole square. So we get this as 4 upon epsilon naught Newton per coulomb, and we have to find out the number of lines per unit area. You can see electric flux per unit area, flux per unit area is our E, which is our 4 upon epsilon naught, and we substitute value of epsilon naught, we get from here our E will be equal to 4 divided by, this is our 8.85 into 10 to the power minus 12, which comes our approximately will be equal to 0.52 into 10 to the power 12, and which we can approximate as 45.2 into 10 to the power 10 Newton per coulomb. So we get this value will be close to 45.2. Next question. It states that two parallel plate capacitors of capacitors C and 3C are connected in parallel combination and charged to a potential difference of 18 volt. The battery is disconnected and the space between the plates of the capacitor of capacitor C is completely filled with the material of dielectric constant 9. The final potential difference across the combination of the capacitor will be. So initially we are having two capacitors and they are connected in parallel with the voltage source of potential difference of 18 volt. So let us call this as C1, which is equal to C, and connected in parallel with our C2, whose value is over 3C, and it is connected in parallel with our voltage source that is given to us as 18 volt. And then battery is disconnected and space between the plates of capacitor C is completely filled with dielectric material. So the space between this C1 is completely filled with the dielectric now, and the other capacitor is as it is. So we have our C2 as it is, and let us call this as C1 prime, and dielectric constant is given to us as 9. So in initial condition we can say that the charge on C1, let us call this as Q1, and charge on C2, let us call this as Q2. So we can say our Q1 will be equal to C1 multiplied by V. C1 is our C and V is our 18. So this comes as 18C. Similarly, we can find out our Q2 will be equal to C2 multiplied by voltage V, which gives us 3C multiplied by 18, giving us 54C. And from here we can find out our total charge. Total charge, that is a QT, will be equal to our Q1 plus Q2, that is our 18C plus 54C. This gives us that the total charge QT will be equal to 72C. And this is all, this calculation is for initial. And this is our final. And final means we have inserted the dielectric and our battery is removed. Therefore we can say final condition. Final condition means dielectric is inserted and battery is removed. Therefore we can say new capacitance for our C1, new capacitance of C1, which we assumed is our C1 prime, will be equal to dielectric constant multiplied by C, giving us 9 times C. And the capacitance of C2 is going to remain same because there is no dielectric in it. So we can say that capacitance of C2 is unchanged, therefore it will be equal to 3 times C, and total charge is also going to remain same. Total charge remains same, that is QT over 72 times C. Now total charge remains the same, but voltage is redistributed. Voltage is redistributed. So we can find out voltage redistributed. Let us call this voltage as our V final, Vf. We are going to find out this Vf. And the capacitors are still connected in parallel. So you can say that capacitors are still connected in parallel. Therefore, we can say thus they share same voltage, that is our Vf. We can find out new equivalent capacitance. So we can say C equivalent nu will be equal to C1 prime plus C2. This comes as 9C plus 3C, giving us 12C. So we can find out our final voltage Vf will be equal to, charge will be our same, that is Q2, and divided by C equivalent nu. This comes as 72 upon C divided by 12C, which gives us C goes by C and 72 goes by 6, giving us 6 volts. So potential difference of the combination will be 6 volts. Next question. It states that a vertical electric field of magnitude 4.9, this should be 10 to the power 5 Newton per coulomb, just prevents a water droplet of mass 0.1 gram from falling. The value of the charge on the droplet will be. So the electric field is preventing the water drop to not to fall. So therefore we can say that if this is our water droplet, in the downward direction we are going to have a mg. So obviously in the upward direction there will be a force due to our electric field, so that the water drop is not falling downward. So under this condition we can say the force due to electric field should be equal to our mg. So we can write that electric field prevents the droplet from falling. Therefore, electric force should be equal to weight of the droplet. Weight of droplet. Electric force is our charge multiplied by electric field, and the weight of the droplet is our mg. We need to find out the charge, so therefore we can say our charge will be equal to mg multiplied by electric field, and we are given mass as 0.1 into 10 to the power minus 3. G is our 9.8. Electric field is given as 4.9 into 10 to the power 5. This comes as 2 into 10 to the power minus 10 coulombs. So the charge will be equal to, one second, there is a, I think it should be 0.9, and this will be over minus 9. Yeah, 8 and 9. Okay, so option B is correct. Next question. It states that a parallel plate capacitor is formed by two plates, each of area 30 pi centimeter square, separated by 1 millimeter. A material of dielectric strength 3.6 into 10 to the power 7 volt per meter is filled between the plates. If the maximum charge that can be stored on the capacitor without causing any dielectric breakdown is 7 into 10 to the power minus 6 coulomb, the value of dielectric constant of the material is. So we are given that dielectric strength is given to us, which is our nothing but our maximum value of the electric field, and the value of maximum charge is given to us. So from here we can find out our maximum voltage. So we can say the maximum voltage will be equal to V max. This will be equal to our E max multiplied by D, that the distance between the plates, a separation between the plates. E max we already know, so we can say our V max. E max is our 3.6 10 to the power minus 7, and the distance between the plates is 1 millimeter, 1 into 10 to the power minus 3. So this comes as plus 7, not minus 7. So this comes as 3.6 into 10 to the power 4 volts. So this is the maximum voltage that will be across the, you can say, the capacitor, plates of the capacitor. Now we can use that our Q is equal to C times V, and from here we can say our C will be equal to our V divided by Q. So Q upon V. Q upon V. Q is given to us as a 7 into 10 to the power minus 6. V we found out is our 3.6 into 10 to the power 4. This gives us 1.944 into 10 to the power minus 10 farads. So this is the value of the capacitance. And with dielectric, we know that the formula, so we can say capacitance of a parallel plate capacitor with dielectric. If that is given as C, which will be equal to our K times epsilon naught A divided by D. C we just found out, we need to find out K, so we can write this as our K will be equal to C times D and epsilon naught multiplied by A. We substitute the value. Capacitance is our 1.944 into 10 to the power minus 10. Distance is our 1 millimeter, that is 10 to the power minus 3. Epsilon naught is our 8.85 into 10 to the power minus 12 multiplied by area is given as our 30 pi into 10 to the power minus 4. So from here this value of K will be approximately equal to 2.33. Therefore option D is correct. Option D is correct. Next question. It states that two identical charged particles, each having mass 10 gram and charge 2 into 10 to the power minus 7 coulomb, are placed, it should be R, not area, are placed on a horizontal table with a separation of L between them. It should be them, such that they stay in limited equilibrium. If the coefficient of friction between each particle and the table is 0.25, find the value of N. Use G as 10 meter per second square. So it says that we have a two charged particle and they are identical. So we can just draw an approximate figure for that. Let us suppose we have two charged particles. This is Q1, and for the sake of convenience, let us assume they are both positive. Okay, and the distance between two is given as L. And it says that obviously they are going to repel each other. So Q1 is going to apply force in this direction. Let us call this as F1, and Q2 is going to apply the force on Q1. Let us call that F2. And if it is entirely in equilibrium, then these forces, we can say friction is going to balance the electric force of repulsion. So we can say in limiting equilibrium, friction balances electric repulsion. So let's find out the value of friction, or rather you can say force of friction. So you can say frictional force that is our Fr will be equal to our mu times mg. This comes as 0.25, mass is given as 0.01 multiplied by 10. So we get our frictional force Fr will be equal to 0.025 newtons. And electrostatic repulsive force electrostatic repulsive force, let us call this as Fe, will be equal to our K times Q square, and distance between the term, that is of L square. So we can write our Fe, value of K is our 9 into 10 to the power 9, charge is our 2 into 10 to the power minus 7 whole square, and divided by L square. This comes as our 36 into 10 to the power minus 5 divided by L square. Therefore, we can equate them. Our Fr should be equal to Fe, which gives us 0.025 is equal to 36 into 10 to the power minus 5 divided by L square. So we can say L square will be equal to 36 into 10 to the power minus 5 divided by 0.025. And this value of L will be coming as 0.025 0.12 meter. So this comes as 12 centimeter. Option A is correct. Correct. Next question. It states that if the charge on the capacitor is increased by 2 coulombs, the energy stored in it increases by 44%. The original charge on the capacitor in coulomb is. So we have to find out the original charge. So let us suppose that the original charge is Q. Original charge is denoted as capital Q, and capacitance is denoted as C. Capacitance is denoted as C. Therefore, we can say energy stored in the capacitor, energy stored in capacitor, that is our U, will be equal to Q square upon 2C. Now the charge is increased by 2, therefore we can say new charge let us suppose we call this as Q prime will be equal to original plus 2. Therefore new energy let us call this as U prime will be equal to Q prime upon 2C Q prime square, and Q prime is our Q plus 2 whole square upon 2C. And relationship between original energy and new energy is also given to us, that is their increase of 44%. Therefore we can say that our U prime will be equal to original energy and its 44%, which will be giving us 1.44 times U. So we know the relationship now between the original energy and the new energy. We can simply substitute U prime as well as value of U. U prime is our excuse me please, Q plus 2 whole square upon 2C, 1.44 multiplied by Q square upon 2C. Here 2C and 2C cancels out, and we just open the square bracket. Q square plus 4 plus 2Q is equal to 1.44 times Q square. So this will be giving us a quadratic equation, and we have here Q square and Q square. So this comes as 0.44 Q square plus 2Q, sorry, not plus but minus 2Q, and minus 4 is equal to 0. So therefore we are going to get two value of Q. One value of Q will be our 10 and other value of Q will be our minus 0.91. Obviously this is our invalid because charge is quantized. So we get that value of Q is our 10. I think that was only asked. Yeah, option A is correct. option A is correct. Next question. It was asked in the advanced, means we already did all the questions. Now we are going to solve for the advanced. So in the first advanced question, it states that in the following circuit, C1 is 12, C2 and C3 is same, which is 4, and C4 and C5 are same, that is 2 microfarad. The charge stored in C3 is dash. Basic circuit is given to us. We have two voltage sources, 6 and 2 volt, and C1 and C2, C3, C4 are connected in the circuit. So we have to find out the, you can say, charge stored in C3, which is this capacitor. So first of all, we can just simplify this given circuit, and it can be redrawn something like this. And we can just, this will be our C2, and we have our C3. We can draw it like this. So this will be C3, and then we have our C4, and finally we have our C5, and it is connected to a voltage source of 2 volt. And from here we can say that our this here in the entire, this will be also voltage at this point will be 2 volt, this will be also 2, this will be also 2, and this will be also 2, and this will be also 2, and this here is C1, and to the left of the C1 we are going to have a 6 volt, because all these C2, C3, C4 and C5 are in parallel, and on the lower part everything will be 0. So therefore we can find out the amount of charge that will be stored on our C1, because we are given that C2 and C3 are same. So this is a 4 and this is also a 4. C4 and C5 is given to us 2. So this is about 2 microfarad, and this is about also 2 microfarad. And so this is our 4 microfarad, 4 microfarad, 2 microfarad and 2 microfarad. So we can find out the charge on C1. Charge on C1, and for C1, let me draw it here. So on the right side we are having a voltage of 6, and on the left we are having a voltage of 2 volts, and our C1 is given to us as 12 microfarad. So we can say charge on C1, which is, let us suppose, given as Q1. So we can say our Q1 will be equal to potential difference across the capacitor multiplied by its capacitance, that is C1. Potential difference across the capacitor is 6 minus 2. So this comes as 6 minus 2 multiplied by 12, giving us 48 microcoulomb. Okay. And we need to find out the charge stored on the our C3. So let me, you can say, name this. So this is 6 volt, and we are interested only on this part. So let me redraw it again, and okay, much more better option is because we have 2 volt supply also. So let's find out the equivalent capacitance of this entire, the equivalent capacitance of this entire part, because here we are having 2 volt also. So we can say that our equivalent capacitance of C2, C3, C4 and C5, and let us call this equivalent capacitance as C equivalent. All these capacitances are in, you can say, parallel. So that will be coming as C2 plus C3 plus C4 and plus C5, giving us 4 plus 4 plus 2 plus 2. So we get our C equivalent will be equal to 12 microfarad. Therefore, we can draw an equivalent circuit for that, and so this is our equivalent circuit. This is our C1, which is having a 48 microcoulomb, and we have voltage, that is V, here it is 6, and this we found out C equivalent, which is about 12 microfarad, and this is supply voltage of 2. Okay, next we are going to find out for, let me draw a loop, and that loop, let me name it, this is suppose our A, this is our B, and this is C, and this is D. So we can say in loop A, B, C and D, so we can say in loop A, B, C and D, we can write this as plus 6 minus 48 divided by C1, that is our 12 micro, minus Q3, that is a charge on C3, and its value is given to us as 4 micro, will be equal to 0. And we can just solve it. Here we can say this will be coming as our 6 minus, this will be 4 minus Q3 divided by 4 micro is equal to 0, and this comes as our 2, and we get this as Q3 will be Q3 by 4 micro will be equal to, this is minus and minus of 2, which gives that Q3 is equal to 8 microcoulomb. So this is the charge on C3, that is our 8 microcoulomb. Next question. It states that a medium having dielectric constant K greater than 1 fills the space between the plates of parallel plate capacitor. The plates have large area and the distance between them is D. The capacitor is connected to a battery voltage V as shown in figure A. Now both plates are moved by distance D by 2 off from their original position as shown in figure B. In the process of going from the configuration depicted in figure A, that in figure B, which of the following statements is or are correct? So we are given two figures, figure A and B. In figure A, dielectric occupies the complete space between the plates, whereas in figure B, the plates are moved further away by a distance of D by 2. So therefore, this entire distance between the plates now comes as 2D. And dielectric, so on the left and right side, there will be presence of air and voltage supply is still connected with the plates. So first of all, we have to find out which of the statement is or are correct. Therefore, in the first case, let us call the capacitance of this capacitor is our CA, and let us call this as CB. So you can see from figure A, we can write our CA will be equal to K times epsilon A divided by D. Area of the plates will be same in both cases. Now, from figure B, we can say that the dielectric is only occupying the distance D, and to the left and right we are having, you can say, air as a dielectric whose dielectric constant is our 1. Therefore, we can say we are having two capacitors which are connected in series. And from figure V, we can say two capacitors are connected in series. Let us call these two capacitors as C1, first one, and which is because of the dielectric. So this is our C1, and this air we can just combine them because here the distance is same as well as area is same. So because of the air, let us call them as C2. So therefore C1, it comes as K epsilon A divided by D, and because of the air we get this as C2 will be equal to epsilon A and also divided by D. Therefore, we can say our equivalent capacitance that is by CB, these are in series, so we can see equivalent capacitance will be our 1 upon CB is equal to 1 upon C1 plus 1 upon C2. We substitute the value, we get 1 upon C1 is equal to, 1 upon CB, C1 is our K epsilon naught A, and this comes as D plus epsilon naught A and D. So we can take this as common, and D epsilon naught A will be common, and this comes as our 1 upon K plus 1. Therefore, our CB will be equal to our epsilon naught A upon D and multiply by 1 upon K plus 1. And from CA is our K upon epsilon naught A upon D. So we can just find out their ratio, and we can write that our CB upon CA, CB is our epsilon naught A upon D, and this is 1 upon K plus 1, and C is our K epsilon naught A upon D. And this epsilon naught A D cancels out, so this comes as 1 upon K, and we can take K as LCM, so this comes as K upon 1 plus K. Here K and K cancel out, this comes as 1 upon 1 plus K. So we found out that the ratio of capacitance of CB to CA is 1 upon 1 plus K. So let us check the option which states that the electric field inside the dielectric material is reduced by a factor of 2A. So let us find out whether this option is correct or not. So we can say option A. So for figure A, from figure A, the entire gap is filled by dielectric. Therefore, we can say that electric field EA will be equal to our potential difference V divided by D. And the field inside dielectric, or we can say electric field inside dielectric, electric field inside dielectric, let us call this as E dielectric, will be equal to electric field in our vacuum or without dielectric, which is our EA, and divided by K. So we get our E dielectric will be equal to our V divided by K multiplied by D. This is with respect to figure A. Now we come to the figure B. In figure B, one part is covered with dielectric, other part is our with respect to air, or we can say vacuum. Therefore, we are going to have two values of electric field because and the thickness is same. First of all, let us call this as our E1, and this E1 is for our vacuum, which will be equal to our V1 divided by D, and our E2, which is because of our dielectric. and that will be equal to our V2 divided by D. And since they are connected in series, so you can say since connected in series, we can say our V will be equal to V1 plus V2, and our relationship between E1 and E2 we can also write. We can write that our E2 will be equal to E1 upon K, or from here we can say that our V2 will be equal to our E2 times D, and we can just substitute it. We can say this will be E1 upon K times D. Therefore, total voltage V, we can write this will be our E1 D plus this will be E2 D, and E2 D we found out, let me write it here, E2 D, we can substitute E2 D as E1 D plus E1 D divided by K, and we can take E1 D as common, so this comes as E1 D 1 plus 1 upon K. So from here we can find out electric field, that is our E1 will be equal to V upon D multiplied by 1 upon 1 plus 1 upon K, and we found out our E1, so we can easily find out our E2. E2 will be equal to our E1 by K, so this comes as our V upon K times D multiplied by 1 upon 1 plus K. But we just, yes, so let us call this equation number 1. And one second, E2 one second, there is to K here because it is a dielectric, yes. And so we know that our E2 is V2 by K times D. Let us call this as equation number 2. So we can say that our from equation 2, we know that our E2 is equal to, there is some, one second. Electric field V upon D E A upon K, so this comes as E dielectric V upon D, and E2 is also because of our dielectric, and this comes as our my mistake, one second. Let me write it here. So we found out that our E2 is equal to 1 upon K multiplied by 1 upon 1 plus 1 upon K, and this comes as V upon D. And we know that our original E2, original electric field, is our V upon K times D. Therefore, we can write that our new electric field because of the dielectric will be equal to this, will be our we can just modify the equation and we get this as our K upon K plus 1 multiplied by 1 upon K multiplied by V upon D. And here K and K cancels out. This gives us V upon K plus 1 times D. We need to find out the reduction. Therefore, we can say that the old divided by new, and old is our V upon K times D divided by new is our V divided by K plus 1 times D. So this comes as our K plus 1 divided by K. So the reduction is, we can say that it is written as electric field inside is reduced by a factor of 2K. So reduction is there, but the factor is our not 2K. So option A is incorrect. Option A is incorrect. Please keep in mind that we have our, this was our old, okay, let me write in bracket. So this is our old electric field and this we found is our new electric field, and this is new with respect to dielectric. And this is old, and this is also with respect to dielectric. I think, yeah, this will be K. I erased it. Okay. So reduction is there, but it's not by a factor of 2K. So the option A is incorrect. And it says that the capacitance is decreased by a factor of 1 by K, 1 upon 1 plus K. Okay, so which we just here found out. So this is our option B is correct. B is correct. So option B is correct. It says the voltage between the capacitor plates is increased by a factor of K plus 1. Okay. But the voltage across the capacitor remains constant. Okay, because it is connected to a V, so it is going to remain V. So option C is incorrect. And it says that work done in the process does not depend upon the presence of dielectric material. So we are going to find out what is the effect of insertion of the dielectric on the work done. Work done is nothing but how the energy is going to change. energy stored is going to change. So you can say option D. And so we can say our initial energy and initial energy means with respect to figure A. Let us call this as UA, which will be equal to our half CA V square. CA we already know, UA is equal to half times this comes as K epsilon A divided by D multiplied by our voltage square. And final capacitance we also know, so we can find out the final energy. That is figure B. So we can say where UB is equal to half CB V square, because voltage is same, CB we found out. So we can say our UB will be equal to half CB is our epsilon A, and this is our D 1 plus 1 upon K times V square. So we are going to find the work done, that is the difference between the energy. Work done, that is our delta U will be equal to our UB minus UA, and which we UB is our half epsilon A D 1 upon K V square, and UA is our half epsilon A, and this is our K times and D multiplied by V square. And we can take here as common, so we get up a half epsilon A D V square, and this comes as K upon 1 plus K, and this is come as minus of K. And we can take this as LCM, so this comes as our half epsilon A V square upon D, and this will be K minus of minus K, and this comes as minus K square divided by 1 plus K, and this K and K cancel out. So this will be coming as magnitude only. If you are interested, it should be ideally VA minus VB, but anyways, this comes as our half epsilon A V square upon D, and this is our K square and 1 plus K. And option D, it states that does not depend upon the presence of dielectric, but dielectric basically means dependent upon K. So this option is also incorrect, because work done contains our dielectric constant, that is K. Okay, we have K in the numerator as well as in denominator. So we can say option D is incorrect. Next question. We are given 6 charges are placed around a regular hexagon of side length A as shown in the figure. 5 of them have a charge q and the remaining one has a charge x. The perpendicular from each charge to the nearest hexagon side passes through the center O of the hexagon and is bisected by the side. Which of the following statements is or are correct in the SI unit? So basic figure is given to us. We have a hexagon and we have, you can say, 6 charges and 4 of them are on the perpendicular bisector of the sides. So we can just draw the perpendicular bisector. And other two also perpendicular bisector. And we have to find out if we place different value of charges, q minus q plus 2q and minus 3q at x. We have to find out how the magnitude of electric field as well as potential is going to change. So let me redraw the figure and let me draw it here only. So here we have to clearly see that we are having these diagonally opposite charges. Okay, let us call this as A, B, C and D, and let us call this as P and this as our Q. And these are in the perpendicular through the center O and bisected by the side. Okay, and we can just complete this something like this. And from here this is center O, and let us call this point as our O prime. So we are given that the distance of PO prime and OO prime is equal. Okay, so we are given that our PO prime is equal to our OO prime, and let us call this distance as R. So this is R, so this will be also R. So this distance will be our R. Similarly, on the opposite side also, these two will be same, and this is our, let us call this as O double prime. So we can say our O double prime will be equal to our O double prime x, and that will be also equal to our R. Okay, so first of all, we clearly know we already know the formula for the electric field as well as the electric potential. So we can say electric field due to electric field at a distance r due to, first of all, let us take positive charge, so we say plus q, the electric field will be over E is equal to K Q upon R square, and because of the and its direction, okay, because direction will be also important here. So this is a plus Q, and this is a point, and the distance between them is given as R. So electric field in case of the positive charge will be in this direction, okay, that is away from the charge. Whereas if we are having negative charge, the magnitude of electric field is going to remain same, that is electric field will be equal to K Q upon R square, but the direction of electric field is going to change now. This is a minus of Q, and this is a point where we are going to find electric field, but in this case the electric field will be in the opposite direction, that is towards the charge, okay? And distance is still the same. Similarly, we can write for the potential. You can say potential at a distance r due to, first of all, we have a positive charge, so its potential is our V, so that will be coming as K Q upon R, and when we have this as minus Q, this will be coming as K minus Q upon R. So this is the basic formula for our electric field. So this will be electric field for positive, and the negative it will be the towards the charge. So if we see clearly, let me draw the figure. We are having these four charges, that the charge at A, B, C and D, they are all positive charge. Therefore, we need to find out in every case the electric field or potential is to be found at the center, that is our O. So we can say for charges placed at A, B, C, D. So this is our center O, and we have the charges which are diagonally opposite to each other. So this is our Q charge, this is also Q, this is point A, B, this is also our Q charge, C, and this is also Q charge, that is our point D. And the electric field we know will be our, for a positive charge, will be away from the charge. So which basically means that the electric field because of charge A will be in this direction. So this will be over EA, and we are going to have this will be over EC. Similarly, we are going to have over EB, and this will be over ED. So net electric field because of all these positive charges will be equal to 0, because their magnitude is same but direction is opposite. So for the charges placed at A, B and C and D, the net electric field at O, let us call this as E net, will be equal to electric field due to A plus electric field due to B. Let me write it. This is our E net will be equal to electric field due to A plus electric field due to B plus electric field due to C and plus electric field due to charge at D. But they are equal and opposite to each other. Okay, so we can say that if this is our EA, so if EA is taken as positive, obviously EC will be our negative. So this is going as minus of EC. Similarly, if we take EB as positive, ED will be taken as negative, and their magnitude are same. Therefore, we can write this will be coming as equal to 0, because our EA is equal to EB is equal to our EC is equal to our ED. So net electric field due to all these charges A, B, C and D is equal to 0. So now, other than these 4 charges, we are also having the charges that is, which is our point P, and other charge is at point X. So this is our X, and the distance is our 2r, and here also it is our 2r. So when X is said to be, in the first case, is said to be taken as plus Q. So we can say on the first case, rather we can say option 1, option A states that our X is equal to plus Q, and P is already having a charge of plus Q. So charge at P is fixed, and for option A the charge at X is our plus Q. Therefore the electric field, because of this X, will be in this direction. Let us call this as a EX, and for our P will be in this direction. Let us call this as a EP. So in this case also, because the charge as well as, so we can say our net electric field we can write, let us call this as E in this case, will be equal to our EX plus EP, and the direction of both are, you can say, opposite. So one will be positive, another will be negative. So let us take that our EP is our negative. Okay. And charges same, the distance between them is same. Therefore we can say that from the figure also our EX will be equal to our EP. Therefore our net electric field, that is our E, will be equal to 0. So we found out that the net electric field due to the charges placed at A, B, C, D is equal to 0, and the net electric field due to the charges which are placed at X and P is also equal to 0, and this is possible for X is equal to plus Q. Therefore option A is correct. And for option B, when X is equal to minus Q, in this case also the net electric field due to A, B, C and D is not going to change, that will be still 0 because charge at X is only changed. So this net electric field is 0 for our part B also. So we are interested in option B. Option B gives us that our X is equal to minus Q. So we can just once again draw the figure. So this is a center O. This is point P, which is having a charge of plus Q, and this is our X, which is now having a charge of minus Q. And we just said that in case of this minus, the electric field will be towards the charge, so we are going to have this as EX, and because of positive charge we are going to have EP. In this case the direction of EP as well as EX is same. Okay, direction of EP and EX is same, and the magnitude will be still same because distance is a 2r. This is about 2r and this is also over 2r. So we can say our EP is equal to our EX. And net electric field that is our E will be equal to our EP plus EX because they are in same direction. Therefore we can write our E will be equal to, this will be our EP will be equal to K Q upon 2r square, and they are same, so multiply by 2, which comes as K Q 4r square multiplied by 2. This 4 goes by 2, so we get our electric field, our E is equal to K Q upon 2r square. Now we have to find out the relationship between our R as well as A. A is our side of the polygon, hexagon. So let me draw one part of that side of hexagon, and this is our center O, and we have taken this is our R. Side of hexagon is our A. And in case of hexagon, let me draw it other side also. This angle will be over 60 degree, and this side will be perpendicular bisector, so this will be also 60 and this will be also 60. And similarly on the other side also we are going to have this angle as 60, so this angle will be also 60. So this is equilateral triangle, each side is equal to A. Okay, let us call this as our, this is O and this is S and this is our T. So we can say that triangle STO is equilateral. Triangle STO is equilateral with each side A, with each side will be equal to A. And we can just take a right angle triangle. So this is our R, and equilateral triangle, this is our A. So this will be our right angle triangle. This is 90 degree, this is R, this is A, and this we are having a 60 degree. So we can say sine of 60 will be equal to our R upon A, which gives us that our R is equal to square root of 3 divided by 2 times A. And we are going to substitute it in this equation. Therefore, we can say that our net electric field E will be equal to K is 1 upon 4 pi epsilon naught. This comes as our Q divided by 2 multiplied by 1 upon R square, and R square comes this as 3A square divided by 4. This 4 goes by 4, and this comes as our Q upon, this will be 6 pi epsilon naught A square. So this will be net electric field 6 Q upon 6 pi epsilon naught A square. Option B is correct. Option B is correct. Okay, now we are going to find out the potential. And the general formula for the potential is our, where it is, okay. So potential is with respect to the sign. For plus Q, it is plus Q, and for minus Q, this will be coming as minus Q. So therefore, A, B, C, D are all having the same charges, that is plus Q, and in the first case it says that, okay, X is 2Q. So let me draw the figure. So we are having, this is a center, so this is a plus Q, and this is also plus Q, and similarly on the other side plus Q as well as plus Q. So this is A, B, C and D, and point P is also having a plus Q, and our X in this case is said to be having a charge of plus 2Q. Plus 2Q. So it means the potential at center O potential at center O, let us call this as V naught. So our V naught will be equal to potential due to charge A plus potential due to charge B plus Vc plus Vd, and it will be then potential due to point P and potential due to point charge at X. This A, B, C, D and P all are having plus charges. So we can say V naught will be equal to 5 times, and the distance is our same. So we can say this will be KQ upon 2R plus. In case of our X, now the charge is 2Q. So this comes as K 2Q divided by 2R. And we can write here V naught. This will be coming as we can take kq upon 2r is common, so this will be 5 plus 2 and this will be 7. We substitute value of r as well as k, so this comes as 1 upon 4 pi epsilon naught. We have this as 7 q divided by 2, and this is our 1 upon r, and r we found out is our square root 3a divided by 2. So this comes as square root 3a divided by 2. Here 2 cancel with 2, so we get our V naught will be equal to, this will be 7q, and we have this as 4 under root 3, this comes as pi epsilon naught a. So this is our V naught when x is having a plus 2q charge. So option number C is also correct. Option C is correct. And in the D option, instead of this plus 2q, now the charge is x is equal to minus 3q. So in this case, still we can write that when for x is equal to minus 3q, potential at the center whichever V naught, so we can write V naught will be equal to VA plus VB plus VC plus VD plus VP and plus Vx. All these charges are same. So once again we can write this will be 5 times k q upon 2r. But in case of this x, we are having a charge of now x is equal to minus 2q. So we can write this as plus k minus 2q divided by, sorry, minus 3q. Minus 3q divided by 2r. So we can write this as V naught. We can take kq upon 2r is common. This comes as 5 minus 3 and it will be equal to 2. So here 2 and 2 cancel out, and we can just substitute value of k, which comes as 1 upon 4 pi epsilon naught. This is our q, and r is square root of 3a divided by 2, and 2 and 4 goes by 2, so we get our V naught will be equal to q upon 2 root 3 pi epsilon naught times a. So this is when charge is minus 3q. And option clearly gives us that this is incorrect. So option D is incorrect. Option D is incorrect. Next question. It states that a charge q surrounded by a closed surface consisting of an inverted cone of height h, base radius r, and a hemisphere of radius r as shown in the figure. The electric flux through the conical surface is nq6 epsilon naught the value of n is. So here basic figure is given to us. We are having cone and we are having a hemisphere, inverted cone rather, and there is a charge q right at the center, and the radius of the cone as well as the hemisphere is same, and height of cone is given as h. So we are going to use here Gauss law, and we have to keep in mind that the charge is enclosed by two different surfaces. One is our hemisphere, other one is our cone. So we can say that total surface, which is our hemisphere, plus cone, is closed, and charge q is at the center. Therefore, by Gauss law, we can write that the flux total will be equal to closed surface electric field for a small area dA will be charge enclosed divided by epsilon naught, and this total flux will be distributed for both our hemisphere as well as for the cone. So we can also write that this flux is distributed between the hemisphere and cone. In what ratio it is distributed, we are not aware. That will be more or less dependent upon the solid angle. But from here we can write our phi total will be equal to flux distributed in the hemisphere plus flux distributed in the our cone, and that will be equal to our q upon epsilon naught. And like I said, this distribution will be proportional to or dependent upon the solid angle. So you can say the electric flux enclosing a charge is proportional to the solid angle subtended by the surface at the location of the charge, to the solid angle subtended by the surface at the location of the charge. At the location of charge. Therefore, we can write based on this explanation that the flux will be equal to our Q upon epsilon naught multiplied by solid angle and solid angle subtended divided by the total solid angle for the complete sphere. And for any portion for the closed surface, for any portion of closed surface, we can write that the flux enclosed by the surface will be equal to charge upon epsilon naught multiplied by solid angle of the surface divided by 4 pi. Now let's find out what will be the solid angles for the surface, because 4 pi we need to find out this solid angle because of the surface. So first is our hemisphere. So you can say solid angle of the surface, and first is our hemisphere. And for hemisphere we can write that the solid angle of the hemisphere will be equal to our 2 pi. And next is for our cone. Therefore, for the cone, so this is our one part of the cone, and we are given that this is our R and height is our H. So therefore, if this angle is our theta, so we can say our tangent of theta will be equal to R upon H. And from here we can write our cos of theta will be equal to H upon R square plus H square and its square root. So its solid angle of the cone will be over 2 pi 1 minus cos of theta. Therefore, the total solid angle let us write this as total is equal to angle because of the hemisphere plus angle because of the cone. So we substitute, we get this as solid angle total will be equal to over 2 pi plus 2 pi 1 minus cos of theta, which gives us that 4 pi minus 2 pi times cos of theta. But we can say that our the surface must fully enclose the charge, so therefore the total solid angle must be 4 pi. You can say, but since the surface must fully enclosed the charge, therefore total solid angle is 4 pi. So from here we can write that our phi t is equal to 4 pi, and value of, sorry, not phi t but solid angle t is also over 4 pi minus 2 pi cos of theta. So this comes as our 4 pi minus 2 pi cos of theta. So here this 4 pi cancels out. So this gives us that cos of theta is equal to 0, or we can say the value of theta is equal to 90 degree, which basically means that it will be treated as a flat cone. So it means if the cone is flat, so we can write that the cone is a flat cone, or we can say that flat cone, which means the apex angle is 180 degree. The apex angle is 180 degree lying in the same plane as the hemisphere base, Therefore, we can say that the total geometrical surface is hemisphere plus flat cone, which basically gives us a full sphere. Therefore, we can say that we know that for the full sphere, the solid angle will be 4 pi. So therefore, we can say the hemisphere solid angle will be equal to 2 pi, as well as for cone will be also over 2 pi, which we already discussed at the start. Now we are going to find out the flux. So we can say our phi total, which will be equal to, by Gauss theorem, Q by epsilon naught. And from here we can say our flux for the hemisphere will be equal to our Q upon epsilon naught, and this will be our solid angle for the hemisphere divided by 4 pi. And we substitute the value, we get it as flux for hemisphere is equal to Q upon epsilon naught. Solid angle for hemisphere is 2 pi, and this comes at divided by 4 pi. Pi and 4 goes by 2, so we get our flux through the hemisphere will be equal to Q upon 2 epsilon naught. And of course cone is having the same solid angle, so from we can also write it that our flux for the cone will be equal to Q upon epsilon naught multiplied by solid angle for the cone and divided by 4 pi. So we get this as Q upon epsilon naught. Solid angle for the cone is about 2 pi divided by 4 pi. Pi and this goes by 2. Therefore we get flux through the cone will be equal to Q upon 2 epsilon naught. And we are given that the flux through the cone is given to us. So we can equate this is given as our N Q upon 6 epsilon naught. And we need to find out the value of N. So here we can say our Q epsilon naught and 6 goes by 3. So this gives us that the value of N is equal to 3. So the value of N is equal to 3. Next question. It states that in the figure inner, that is shaded region A, represent a sphere of radius Ra which is given as 1, within which the electrostatic charge density varies with a radial distance r from the center as rho of A is equal to K times R, where K is a positive. In the spherical shell B of the outer radius RB, the electrostatic charge density varies rho B is equal to 2K upon R. Assume that dimensions are taken care of, all physical quantities are in their SI units. Which of the following statements is or are correct? So in this case, in the options we are going to take various values of our RB, radius of B, and find out electric field, electric potential, total charge, and electric field just outside B and just outside B, okay, for various value of RB. So we are here given as figure is given to us. So we have a inner sphere that is represented A, radius Ra, which is equal to 1 unit, and we have B, radius is RB, but their charge densities are different. So this is having a rho A and this is having a rho B. Okay. And so first of all, we are going to find out what will be the charge in region A. Okay. Then we are going to find out the charge in region B. So we can say that the charge in region A here the density rho A is our K times small r. Therefore we can say that if the charge in region A is given as QA, then QA will be equal to integration of from 0 to 1, because value of R is given as 1, and this is our rho A times our small volume V. volume we know is our 4 pi 3 pi r cube. We can just directly solve it. So this comes as 0 to 1, this comes as kr, and it will be coming as 4 pi r square, and this is our dr. We can take common, we get this as 4 pi k 0 to 1, and we have this r square dr. This will be coming as r cube by 3, and one second. Yeah, kr, sorry, my mistake. This is cube. So this will be coming as r4. So this comes as 4k 1 upon 4, and here we have r4 from 0 to 1. So 4 goes with 4, and this comes as 1. So we get our charge will be equal to pi times k. So this is value of the QA. Similarly, we can find out the charge in region B. Charge in region B, and the charge density, that rho B, is given to us as 2k upon r. 2k upon r. So we can say charge in B will be equal to our, and this B, it starts with, so our B, we can, this is our region B. So here we are having 1, and this is our radius RB. So the limits of integration will be 1 to RB, and this comes as our rho B, and we have our dV. So this is our rho 1 RB. This comes as 2k upon r, and we get here as 4 pi r square times dr. R goes by this square, and we can take common, will be coming as 8 pi k, and integration of 1 to rp, and we have this is r dr, and this will be coming as r square. So we get this as 8 pi k divided by 2, and multiply by, here we have our r square, 1 to rb are the limits. So we goes by this 4. So we get our charge QB will be equal to 4 pi k, and it will be coming as RB square minus 1. Capital B, not small b. So we found out the value of charge on the sphere as well as charge on sphere on the shell. So therefore total charge let us call this as QT will be equal to QA plus QB, or rather again total charge enclosed. So we get this as QT, QA is our pi k, QB is our 4 pi k, and we have this is RB square minus 1, and pi k we can take as common. So we get this as our total will be equal to pi k, and this comes as our 1, this will be our 4 RB square minus, and this will be 3. So this is our total charge enclosed. Now let us check one by one for various values of, you can say, RB. So for first value of RB, option A gives us that our RB is equal to square root of 3 divided by 2, 3 by 2. So therefore we can say we require RB square. So we can say our RB square will be equal to 3 by 2. So we can say our charge total Qt will be equal to pi times K, and this comes as 4 multiplied by 3 by 2 minus 3, and this goes by 2, so it comes as 6 minus 3, which will be equal to 3 pi K. And in the first part, electric field is 0 everywhere outside B. Okay, so charge is not equal to 0. So it means the electric field because charge enclosed is not equal to 0, so electric field will not be equal to 0. So option A is incorrect. A is incorrect. And for say electric potential juts outside B is K upon epsilon naught. So we have our option B. Our RB is equal to RB is 3 by 2. RB is 3 by 2. So we get our RB square will be equal to 9 by 4. Therefore we can write our total charge Qt will be equal to pi K 4 times 9 by 4 minus 3. 4 goes by 4, and this comes as 6 pi K. And we need to find out the potential just outside the spherical surface. Therefore we can say potential, that is a V, will be equal to 1 upon 4 pi epsilon naught. Our charge enclosed, that is Qt upon RB. This comes as 1 upon 4 pi epsilon naught. This is our 6 pi K, and RB is our 3 by 2. So we can say that our this comes as 12, so this comes also 12, and pi also goes, so this comes as K upon epsilon naught. So option B is correct. B is correct. Next value of RB is our option C, that is 2. Option C, value of our RB is about 2. So therefore our RB square will be equal to 4. So once again, we total charge Qt will be equal to our pi K, and this comes as our 4 multiplied by 4 minus 3. This comes as 16 minus 3 is equal to our 13 pi K, which is option is 15 pi K. obviously it is. So option B is correct. Option C is incorrect because it is not 15 pi k. You can say option C is incorrect. Option D, our RP is our 5 by 2. So our RP square is equal to 25 divided by 4. So therefore total charge Qt is equal to pi k, and this comes as 4 times 25 divided by 4 minus 3. 4 goes by 4, and this comes as 22 pi k. So we have a total charge. So we have to find out the field, electric field rather. So we can say our electric field E will be equal to 1 upon 4 pi epsilon naught, and this is our charge total upon r square, which is nothing but rb square. So we get this 1 upon 4 pi epsilon naught multiplied by 22 pi times k, and rb square is 25 upon 4. So this is pi, 4 and 4 goes away, and this comes as our 22 upon 25 k upon epsilon naught. So option D is also incorrect. Option D is incorrect. So option D is also incorrect. So only option B is correct. Next question. It states that a disk of radius r with a uniform positive charge density is placed on the xy plane with its centered origin. The Coulomb potential along the z-axis is Vz sigma r square plus z square minus z square root up till here divided by 2 epsilon naught. A particle of positive charge q is initially placed at rest at a point on z-axis with z is equal to z naught, and z naught is greater than 0. So it means on the positive z-axis. In addition to the Coulomb force, the particle experiences a vertical force F, which is minus ck k unit vector, whereas with c greater than 0. Let beta is equal to 2c epsilon naught q multiplied sigma. Which of the following statement is or correct? So basically we are given various values of beta as well as z naught, and we have to find out whether the particle reaches the origin or it returns back to its original position. Okay. And this entire discussion is based on the concept of the energy. Okay. So if the energy at the origin is less than the energy at our z naught, so it will be going to reach origin. If it is reverse, then it is going to return its original position. So we have to find out the difference in the energy. So let's find out. Okay, and the particle is placed at the position of our z. So it is going to have energy because of its position, which we can also call as a potential energy because of the position, and it is also going to have a energy because of this potential difference. So we can say total potential energy, total electrostatic potential energy, let's write out potential energy only, total potential energy, suppose that is given as U of Z, then we can say that our U of Z will be equal to charge multiplied by the potential plus C times Z. V of Z we already know, we substitute it, we get this as Q sigma divided by 2 epsilon naught, and we have this as R square plus Z square square root minus Z, and this way we have plus CZ. And and we know that our, if we multiply it inside, no, one second, one second, there is some, beta is given to us as okay, and if you open the bracket we get this as Q sigma divided by 2 epsilon naught, and this will be a square root of our R square plus Z square minus, and this will be equal to our one second. See, okay, beta is given to us, yes. So we know that our beta is equal to 2C epsilon naught upon Q times sigma, and from here we can say that our C will be equal to this, we have Q sigma upon 2 epsilon naught, and this will be times our beta. We substitute value of C, we get this as our U of Z is equal to Q sigma upon 2 epsilon naught, and this will be our R square plus Z square minus Z plus q sigma upon 2 epsilon naught times beta and times z. So further we can take this sigma upon 2 epsilon naught common, so we get our u of z will be equal to q sigma upon 2 epsilon naught. We are left with our r square plus z square minus z plus beta times z, and from here we can take z as common, so we get our u of z will be equal to q sigma upon 2 epsilon naught r square plus z square root plus beta minus 1 times z. So this is our energy at, that is a function of z, and we can say that our particle, because initially it said that the charge is released from the rest. Okay, so there is no as such initial kinetic energy present in the charge. So we are given that charge is released from a rest. So therefore it moves depending upon the potential energy difference. It moves depending on potential energy difference. So based on this we can say that if energy at z is equal to z naught is greater than energy at the origin, then the particle can reach origin. Particle can reach origin, and if we have our energy at z naught is less than energy at the origin, then the particle cannot reach origin or returns to its original position. Particle cannot reach origin, or we can say it returns to its initial position. It returns to its initial position. So let us find out our for u of z we already know, so let me write it here. So we have our u of z is our q sigma upon 2 epsilon naught, and this is our r square plus z square root plus beta minus 1 times z, and u of 0 will be equal to q times sigma upon 2 epsilon naught, and putting z is 0, this will be multiplied by r. So for our u of z, because this we are not interested in this portion, we are only interested in this particular variable because it is dependent upon the z. Therefore we can further say that u of z is approximately equal to our r square plus z square and its square root plus beta minus 1 times z. Okay, so we are going to use these two equations. So let us check the options one by one. So first is our option A. Option A gives us that a beta is equal to 1 by 4 and our z naught is equal to 25 upon 7 times r. So first of all, let's evaluate r square plus z square. So we get our r square plus z square plus beta minus 1 times z, and we get this as r square plus 25 upon 7 times r whole square and its square root minus beta is our 1 by 4 minus 1, and this our 25 by 7 times r. We can take r as common because this will be r square and r square, and this is also our r, so we can take r as common. We get this as 1 plus 625 divided by 49 and its square root minus this will be our 3 by 4, sorry, it will be minus 3 by 4, one second. Beta minus, sorry, here it is plus. So this comes as minus 3 by 4 times 725. So this comes as 75 by 28. And we can just approximate it. This will be coming as r, and this will be over 3.72 minus 2.68, which is coming as r is equal to 1.04. And in the second case, for this we can say our u naught is approximately equal to r. So this value, we can say our u of z naught is greater than our u of r, because u of r is our only r and u of z naught is our r 1.04. Therefore particle reaches origin. Particle reaches origin. So our option A is correct. Option A is correct. Come to the option B. Option B gives us that the beta is equal to 1 by 4 and our z naught is our 3 upon 7 times r. Similarly, we are going to find out our r square plus z square, which comes as 3 by 7 r whole square square root minus, and this is plus 1 by 4 minus 1 times 3 by 7 times r. Once again we can take r as common. this comes as our r, and we are left with 1 plus 9 upon 49 square root, and this comes minus, this will be 3 by 4 and coming as 9 upon 28, which gives us r will be equal to 1.087 minus 0.32, which gives us that r times 0.767, which is obviously less than r. So from here we can say our u of z naught is less than u of naught. So therefore it never reaches origin, and option B gives us particle reaches origin, which is not possible. Option B is incorrect. You can say never reaches origin. Or we can say returns back. Therefore option B is incorrect. Incorrect. We come to the option C. Our beta is equal to 1 by 4 and z naught is equal to r upon square root of 3. Therefore we get our r square plus this will be r upon square root of 3 whole square root minus plus 1 upon 4 minus 1, and this comes as r square root of 3. So we can take once again r will be our common, so this comes as 1 plus 1 by 3, which gives us 4 by 3 square root, and this will be minus, we have this as 3 upon 4 root 3, and this will be giving us r is equal to 0.7217, obviously less than r. So therefore does not reach origin. Does not reach origin, or we can say returns back. Returns back to z naught. Therefore our option C is correct. Option C is correct. And option D, states that beta is greater than 1 and z naught is greater than 0. So here we have to make an approximate guess, because exactly it's a little bit difficult to solve, values are not specifically given, but we can make a guess that for our u of z equation is our q sigma upon 2 epsilon naught, and here we are having two factors. One is our r square plus z square root, and other factor is our beta minus 1 times z. So if we see that we can write rather that r square plus z square is going to give, you can say it is growing to at a slower rate as compared to z. So you can say this grows slower than z. We can approximately say, like, if the z of value of z is 2, so this square root might be coming like 1 point something, and if z of value is 4, the square root of this function might be still in 1 point something. Okay, so the increase is much you can say marginal in case of r square plus z square ka square root. But for when beta is greater than 1, so because of this the linear function is going to dominate. So you can say the linear term is going to dominate, and if the linear term is going to dominate, so we can say that both the terms, the first term as well as second term, are increasing. First term increasing slowly, whereas the linear term is going to dominate. Okay, so therefore we can say our u of z increases with z, increases with z. Thus we can write that our u of z naught will be greater than for u of 0, for z naught greater than 0. So it means the particle is released from rest at a higher potential. So from here we can say that particle is released from rest at a higher potential, or in simpler terms we can say that particle reaches the origin. Particle reach origin. Therefore our option D is also correct. Is correct. So this completes the questions from the year 2022, all the questions in part 1 as well as part 2. In part 2 we covered, in part 1 rather, we covered only the mains question. In part 2 we covered the remaining question of mains as well as the question of advance. So this completes all the question from the year 2022. Thank you.